How does a feedback loop improve control system design? Imagine trying to keep a boat steady on choppy water. The boat constantly adjusts its direction based on how much it tilts. That's similar to how feedback loops work in control systems. They help systems stay on course even when conditions change. When designing control systems, especially for robotics and mechanical applications, feedback loops are essential tools. They keep everything running smoothly and accurately. A feedback loop involves several key parts. First, there is the plant, which is the system you want to control. Then, sensors measure the output, like the position or speed of a motor. The controller compares this measurement to the desired value. If there's a difference, called an error, the controller calculates how to fix it. The controller then sends signals to actuators, which make adjustments to the system. This process repeats over and over, creating a continuous cycle of correction. Most feedback systems use negative feedback. This means they oppose any deviation from the target. If the system starts to drift away, the feedback reduces that error, bringing the system back on track. This makes the system more stable and less prone to oscillations. It also reduces steady-state errors, which are small differences that can persist over time. Positive feedback, which amplifies errors, is rarely used because it can cause instability. In robotics, feedback loops are vital. For example, in robotic arms, sensors track the arm's position and speed. The controller adjusts motor inputs to keep the arm moving precisely, even if the load changes or there are external forces. This results in smoother, more accurate movements. Feedback loops also help control systems handle uncertainties, like modeling errors or environmental disturbances. Since the system constantly monitors and corrects itself, it stays reliable even when conditions are not perfect. In real-world applications, feedback control is everywhere. It keeps electric motors running at a steady speed despite changing loads. It maintains temperature in ovens by adjusting heat input based on sensor readings. It guides CNC machines and industrial robots to produce precise parts. It even reduces vibrations in structures by actively damping oscillations. Overall, feedback loops improve control system design by enabling systems to self-correct. They make systems more stable, accurate, and adaptable. This is why feedback is a fundamental part of designing effective mechanical and robotic systems. It's like having a built-in navigator that keeps everything on course, no matter what challenges come up.